we will discuss synchronization. Synchronization is required, is must for a digital communication system. It synchronizes the input locally generated clock with the input signal so that we can receive the bits or the rather data or the information unambiguously. Now synchronization may be classified in broad sense into two groups. One is the bit synchronization, another is the frame synchronization. So first we will consider the bit synchronization. Actually this bit synchronization, rather the bit synchronizers, they are actually extracts the clock information from the data. This is the basic objective of this bit synchronization, because at the receiver side we must sample the incoming signal, and then we have to take the decision that whether that sample, for a binary case, sample is below certain threshold or above certain threshold. Depending on that we will decide whether it is logic 1 or logic 0. But first of all we have to take the sample, and to take the sample we need a clock. And if we expect that clock will come to the receiver in the parallel path, that is a very difficult job. So we have to extract the clock information from the data itself. So that is done with the help of this bit synchronizer. Now bit synchronizer may be divided into two groups. One is called the open loop, another is called the closed loop. These open loop circuits recover the replica of the transmitted data clock from the doing some operations on the incoming data stream. And closed loop comprises the actually this closed loop synchronizers attempt to lock a local data clock to the incoming signal by use of some kind of comparative measurements on the local and incoming signals. Now in closed loop system we use feedback. It is a closed loop means it is a feedback network. So obviously it is expected that closed loop synchronizers performance is expected to be better. Its stability is expected to be better compared to the open loop. It must be closed loop system must give us much more accurate results, and obviously since we have a feedback network, so it must be costly and complex network. So first let us consider the open loop. So we will consider this open loop synchronizer. The various type of circuits are there. So let us take any one of such circuit. Not circuit, it is a block. So first block is the masked filter. Next block is the even low nonlinearity. Next one is the band pass filter, and finally we have the wave shape generator. We are writing as a SGN. This will actually generate the clock shape of the clock will be decided by this one. To understand this, we will consider some example of, say, bipolar data like this. Say this is plus B, this is minus B, or you can call it plus 1 minus 1. So this is the incoming signal, binary, incoming binary signal. When it is passed through the matched filter, since it is square in shape, matched filter output will be triangular in nature. I cannot draw in scale, but it will be something like this. Something like this. Now we will pass it through even law nonlinearity, which is basically function as a rectifier. Full wave rectifier is one of the example of even law nonlinearity. So what it will do, it will keep this part as it is, positive polarity as it is, and negative polarity will be come to the positive side. So instead of this negative side, it will start from this part, then we have this one up to this point, and this one will be converted into positive polarity like this. Next we have original positive polarity, next we have another negative polarity that will be converted into positive polarity, and we have this one, something like this. So this is the output of even law nonlinearity. Now if we analyze properly, we will see that the output waveform of this even law nonlinear device will contain a Fourier component at the fundamental frequency of the data clock. So this frequency component must be isolated or extracted from its harmonics, and that is done with the help of this bandpass filter. So bandpass filter will eliminate the harmonics and it will pass the original fundamental frequency, which is nothing but the clock frequency. So once we have the fundamental frequency, the output of the bandpass filter, we have to generate its proper shape with the help of this kind of saturating amplifier, and the transfer function of this circuit may be written in this way. It will be 1 for x greater than 0 and -1 otherwise, something like comparator. It will compare with 0, and if it is higher then it will be 1, otherwise it will be -1. So it will give us the proper shape. So at the output we will get the rectangular clock. So consider another example. Say this is the input signal, we have a delay network that will produce a delay of half bit period that will be multiplied and the output of this multiplier may be written as empty. Then we have band pass filter, and we have the signal shaper circuit. It will produce the ultimate clock. Here the circuit will produce a Fourier component at the data clock frequency by means of this delay and using this multiplier. Now delay, as you can see, that it is a half bit period, because it is the best value, as it provides the strongest Fourier component. Now this waveform M will always be positive in the second half of every bit period, but will have a negative first half if there has been a state change in the incoming bit stream of ST, and that produces a square wave signal with a spectral component at the data rate and all harmonics, just like this one. So we have to isolate this fundamental component, and that is done by with the help of this band pass filter. And once we get the fundamental component, the wave shaper circuit, just like this one, wave shaper circuit will produce the corresponding clock. It will shape the signal and it will produce the corresponding clock. Let us take another example of open loop bit synchronizer. Input signal is first passed through the low pass filter. Then we have a differentiator, and the output of the differentiator is passed through a nonlinear square law device. The output is passed through a band pass filter and then the wave shaper circuit, just like before. So this is the circuit, or rather block diagram. Here it is first passed through low pass filter to eliminate any high frequency noise terms, because we have this differentiator, and differentiator is basically a high pass filter. So if we don't use this low pass filter, then we will get erroneous result. So we have to pass it through this low pass filter first. Now what this differentiator will do, whenever we get this type of waveform, differentiator will produce spikes. Here we have a spike, here we have a spike, here we have a spike, and so on. These spikes will pass through this square law device, that is a rectifier. So for example, here we have, if we have a positive spike, here we have a negative spike, right? So this square law device will convert all these spikes into positive direction. So after this square law device or rectifier, we will get a train of impulses at a frequency whose fundamental component is the clock frequency, and that is passed through this band pass filter to isolate the fundamental component, and then wave shaper circuit will do its job. That means it will produce the clock, it will shape the clock. So these are the example of few open loop synchronizers. Now we will consider a closed loop synchronizer. The closed loop synchronizer that we are going to study is the early late gate synchronizer. And as I already mentioned, that this type of closed loop, this is a closed loop. Closed loop synchronizers, they are actually tries to lock the locally generated clock signal with the incoming binary signals. So just consider the basic block of this early late gate synchronizer. So here we have two integrators. This is the late gate, output is y1, we will extract the magnitude with the help of this block, absolute value. We have another path, in this path we have another integrator. This one is called the early gate. This output say y2, and we will get the magnitude. So here we get the y1, here we get y2. These two are subtracted actually to produce an error signal. Error signal is y2 minus y1. Then we have, just like PLL, we have a loop filter, and the output is given to the VCO. Loop filter output is given to the VCO, and VCO actually runs this to integrator. So this is the block diagram of early late gate synchronizer. To understand this operation, we will first try to understand when the loop is locked, and then we will try to understand when the loop is unlocked, how it comes back to lock condition. So this is, say, incoming bits. This is the positive, say, logic 1, say. So what early gate will do, early gate will integrate this portion, and late gate will integrate over this portion. So early gate will accumulate the signal within this region, and late gate will accumulate like this one. And since first we are considering that this VCO is under locked condition, so it is obvious that this early gate and late gate will accumulate same amount of signal, equal amount of signal. Since these two gates will accumulate equal amount of signals, means y1 equal to y2. So magnitude of y1 is equal to magnitude of y2. That means this E is now 0. So loop filter will produce corresponding output, and VCO will run accordingly, because since it is already locked, there is no change in the VCO frequency. Now we will consider the other situation where the receiver data clock is little bit earlier. That means here the integration was started just at this point, at the time of arrival of the bit. But here now you will consider that the integration will start slightly earlier time. So early gate will start it in its integration earlier. This is early gate. And obviously late gate will also be shifted little bit. Like this one. But the point is that within this region the value of the bit is negative, and this negative portion will be positive at this point. That means this early gate will accumulate less amount of signal compared to the previous one. Here it accumulates throughout this entire period of integration, but here the accumulation, since this one is negative and this one is positive, so some portion will be lost, it will be compensated. So actually it will gather comparatively smaller amount of signal, whereas the late gate will accumulate the equal amount of energy as before. So under this condition, late gate output Y1 will be greater than the early gate output Y2. So magnitude of Y1 will be greater than magnitude of Y2. Now E, error signal, is Y2 minus Y1. So since Y2 is smaller, so the error signal will be negative. Now once we have negative error signal, that will pass to a loop filter and the VCO input will be reduced. Before it was 0, now we have certain amount of negative voltage, so VCO frequency will be reduced in such a way that VCO input will be reduced, so VCO frequency will also be reduced, because VCO, voltage control oscillator, here this it follows this rule that if input signal is lower, then output frequency will be lower. So if input signal is now lowered, input error voltage, so the output frequency will also be lowered. In such a way, it will come back to its original point of start. Similar thing happens if the situation is reversed. So in short, what we can say, that if the receiver starts its integration earlier, then the error signal will be negative. This negative error signal will produce lowering of the VCO input voltage. That will reduce the frequency of this VCO to reduce, and it retards the receiver's timing to bring it back towards its incoming signals bit timing. So this is how it works, and situation will be just reversed if we have just opposite condition. So this is how this early late gate synchronizer works. Let us now consider the frame synchronization. Frame synchronization is needed at the TDM receiver so that the received multiplex data can be shorted and directed to the appropriate output channel. The frame sync can be provided to the receiver demultiplexer circuit either by sending a frame sync signal from the transmitter over a separate channel. That is almost is a very much difficult thing, or by deriving the frame sync from the TDM signal itself. So that is the job of this frame synchronization. So let us try to understand this frame synchronization. For the sake of simplicity, we will consider the simplest form of frame synchronization. So if we consider that we have number of channels, say we have channel 1 data, then we have channel 2 data, and so on, so up to say channel n. So these are the, we will produce a block of data consists of channel 1, channel 2 and channel n. So this chunk of data we will transmit simultaneously, not simultaneously, serially, one by one. Now we have to identify the first bit of this block, and to identify this first bit of this block, so, and this will be repeated, actually this will be repeated. What we do, we will add a set of, rather a bit stream, say S1, S2, say k number of bits. So at the start of each block of data or each chunk of data, we will add another set of data of k bits. So earlier or later, whatever may be the chunk of data, we have to add this bit stream in front of channel 1 data. That means after this nth channel, again S1, then S2, SK, and then again channel 1 data, then channel 2 data, and so on. So in this way the data will be transmitted. So starting from here also the previous channel or something like that, channel n data. So in this way data is transmitted. So starting from this portion to the end of this block is the frame, and the special data sequence that we use to add in front of this chunk of data is the sync word. And this section is the actual information field. So this is how the TDM data is transmitted frame wise. Now at the receiver we have to identify this sync word. Now this sync word must be chosen in such a way that this data sequence should not be repeated in the channel data information field. Otherwise, this information field will be treated as sync data, sync word. Not only that, a sync word must not be very large, because otherwise it will be the actual information, amount of information will be less, and it will not be very small, so that it will not be identified in a separate fashion. So if we use some very small sync word, tiny sync word, then it may match with the channel data. So the choice of sync data is very, sync word is very important for this particular situation. So let us try to understand the how we can implement this. So this is the TDM input. First of all, we need amplifier and filter to eliminate. Amplifier is used to amplify the signal, and filter is used to eliminate the noise. Next, we have to take the sampler circuit and decision circuit. That whether we are receiving logic 1 or logic 0. But for that we require a clock. So we need a bit synchronizer. Right here. That bit synchronizer will extract the clock. Now we have actual, this is the data. That data is passed through a shift register, serial shift registers. This is first one, this is second one, and number of shift register must be k, because we have chosen k bits of sync words. So up to stage k. The shift registers are also using the same clock. So data will first enter stage 1, then that particular data will go to the stage 2 in the next clock cycle, and so on. Now we can get the data from these shift registers in a parallel fashion through a special circuitry. And we have coincident detector similar to n input AND gate. The output is frame sync. So what happens when we are getting the data, and data is entering through these stages, and we are getting the output here. Now we have to this S1, S2, SK, etc. These are nothing but either they are short or a NOT gate, depending on whether the SI is 0 or 1, rather 1 or 0. That means if SI, ith term of this sync word, if it is 1, then this SI will be simply a short, and if it is 0, then it will be a NOT gate. That means when all the stages are filled up with exactly these sync words, then all the inputs to this coincident detector will be 1. So once we have all the inputs of this coincident detector 1, the coincident detector will momentarily produce a logic, will go to the logic 1 state, which is nothing but the frame sync. If some other data enters in this shift registers, then any one of these inputs will be 0, and under this condition coincident detector output will remain 0. So coincident detector output will be 1 only when all these shift register stages are filled up with the proper sync word that we have, that the transmitter had given. So this is how this frame sync works, frame synchronization works.